Hello everybody, thank you for watching this video. I'm Andres Villa from the Kim Abdullah University of Science and Technology, CAUS, and Pontifical Catholic University of Chile. I'm excited to present our work named vCLIMB, a novel video class incremental learning benchmark. This is joint work with researchers from CAUS, Samsung AI Center Cambridge, and Adobe. Due to the action's diversity and the millions of video data uploaded every day through platforms like TikTok and Instagram, real-world deep learning pipelines rarely involve a single training stage. Instead, they could be trained sequentially in several disjoint video tasks without forgetting the previously learned knowledge. This scenario is known as continual learning. We focus on the most challenging case of it, class incremental learning, where the labels and data are mutually exclusive between tasks. Training data is available only for the current task, and there are no task IDs during the inference. We propose vCLIMB. It is a novel benchmark devised to evaluate class incremental learning in video to promote and facilitate research in this area. Our benchmark includes three well-known video datasets, like UCF101, Kinetics, and ActivityNet. This table provides the main statistics of the scenario we proposed in our benchmark. For each dataset, we create two sets of tasks, one with 10 tasks and the other with 20, which is more challenging because it has a longer series of tasks. Therefore, it offers more chances to forget. Also, for the first time, we propose evaluating a more realistic and challenging scenario using on-stream video data, in this case taken from ActivityNet. In order to evaluate our benchmark, we extend four methods from image domain. The first two are EWC and MIS. These are regularized methods that penalize changes to the most relevant parameters for the previous task. The other two, ICAR and MIG, are memory-based methods that select and store samples of the current task into a memory buffer for future replay. Consistent with image benchmarks, the memory-based approaches significantly outperforms the regularized methods. This table shows that the video instances contain a temporal dimension size that could show large variability. To favor fair comparison between methods, we define the working memory size of the rehearsal methods in terms of stored frames. This creates a new unique scenario of class incremental learning in video data, in which rehearsal methods must decide first what subset of frames should be selected and then decide what video to store according to the selected frames per video. In this case, for simplicity, we uniformly sample the same number of frames per video. However, we encourage future works to focus on this. We also present a novel strategy for rehearsal methods to reduce memory consumption while improving performance. It is a temporal consistency regularization loss represented by the red dashed arrow in the figure. This loss constrains the network to estimate similar representation for the original clip and its temporally downsampled version. Thus, it enables the network to remember from the temporally downsampled version of the previously learned task. We achieve outstanding results with the temporal consistency loss, especially in the dataset that requires more sophisticated temporal reasoning like ActivityNet. On both versions of ActivityNet, trim and on-trim, our regularization loss enhanced the performance by 24% when we save 8 frames. Likewise, it remains close to the best performance with all frames shown in the red dashed line, but with 0.2% of the memory size. In summary, our contributions are: first, we standardize a realistic benchmark for continual learning in video action recognition. Second, we present the temporal consistency loss to reduce the memory consumption while increase the performance. And third, we extend the baselines from the image domain into the video domain. So, thank you very much for watching the presentation. See you in the poster session.